We are continuing our discussion of momentum, and now we're going to talk about types of collisions. So, this is actually types. This is actually one of my favorite things. So, for types of collisions, we're going to start talking about the one that we've already talked about, and that is a completely inelastic collision. Sorry about that. So, in a completely inelastic collision, the most characteristic thing about it is that our objects stick together. That's the most important thing about a completely inelastic collision. Now, we have other collisions. We'll go ahead and talk about all of them. We have regular old inelastic collisions. In this, objects separate. They move apart. I'm going to leave some space to talk about what else is notable about an inelastic collision. And then we have elastic collisions. And in elastic collisions, the objects also separate. So, these are our three types of collisions. Completely inelastic, they stick together. Inelastic and elastic, they separate. But for inelastic and elastic, there is another difference that we really need to talk about. For the inelastic collision, where they separate, kinetic energy is lost. Now, kinetic energy is just motion energy, in that we lose something. Imagine, if you will, it was an old game. You used to throw a tennis ball up against the little thing that you catch it with, the round circle Velcro thing, and if you threw it too hard, the ball would hit and kind of stick as it was coming off, and it just fall off with not near as much energy. Think about it this way. A really good look at an inelastic collision, a really good way to think about that. Let's say we have a wall. We throw a ball towards the wall with a speed of 10 meters per second. In the inelastic collision, the thing hits the wall, bounces off, but it only comes off with anything less than 10 meters per second. 8 meters per second of velocity. We're losing some of this velocity as we bounce off the wall. That's characteristic of something that's inelastic. It doesn't stick to the wall, but it doesn't bounce off completely clean. It's leaving something there. So, in the elastic collision, as far as energy is concerned, we have no loss of kinetic energy. Now, it's not really fair to talk about kinetic energy, and I'm not going to make you do any calculations of that yet, because we're just, well, that's our we'll start that after semester break. But as long as we're thinking about the ball hitting the wall, in this case the ball comes in with 10 meters per second, and it's going to leave the wall with 10 meters per second as well. It's a clean bounce. It has all of the energy coming off the wall that it went into it with. Now, there is another way that we characterize collisions, and this is going to be a little conceptually tough to look at and think about, so I need you to stick with me on it. But the other thing that we do is we look at how do the objects move with respect to the center of mass. we're going to ask ourselves that question about each of these collisions. So, completely, another way we say it is perfectly, inelastic. And so we're going to look at an example here in order to do this. Let me get to where I can draw it. Let's say we have a mass of 5 kilograms moving at 10 meters per second towards another mass, and to make things easy we're going to call it 5 kilograms again, moving at 10 meters per second towards it. Now in this case, and since we're doing this in terms or with respect to the center of mass velocity, the velocity of the center of mass needs to be calculated. So 5 times 10 plus 5, and here we've got times negative 10 divided by 5 plus 5. We see in this case that the velocity of the center of mass is equal to 0. So for this completely or perfectly inelastic collision, these two objects, after they hit, are going to stick together. I'm going to have a 10 kilogram mass. And this 10 kilogram mass, after they hit and stick together, let's look at it. We have 5 times 10 plus 5 times negative 10. That's my initial momentum. Will be equal to 5 plus 5, whoops, 5 plus 5 times our final velocity. So we're going to get, and then that's the final momentum of the system. We know those two things have to be equal. So we'll have 0 is equal to 10 times v final. We see that that thing is moving with a final velocity of 0. It's not going anywhere. So this has a velocity equal to 0. And so for a completely inelastic collision, the velocity of the center of mass is 0, and afterwards the entire mass of the system is moving with the velocity of the center of mass. So let's write that down. Entire mass, actually tell you what, better way to write that. Both masses move with the velocity of center of mass. So for each one of these masses, they now have the velocity that the center of mass had beforehand. That's how a completely inelastic or a perfectly inelastic collision works. So let's look at the next one. Just inelastic. So for the inelastic collision, I'll tell you what, to make things easy, we will use the same two masses so that we already know stuff about it. So we have 5 kilograms moving at 10 meters per second this way. Another 5 kilograms, and it's moving at 10 meters per second in the opposite direction. And they're going to hit, and they're going to separate. And so we'll have one of them, this one, moving back at 2 meters per second. And the other one will have to move in this direction. And we'll find that in a second. So we know that the velocity of the center of mass here is 0. And one of the things we said was that the velocity of the center of mass does not change, so after they hit, I know that the velocity of center of mass also has to be 0. So in order to look at this, we have 5 times 10 plus 5 times negative 10 is equal to 5 times, this time -2, plus 5 times his final velocity. We have 0 equals -10 plus 5v. We have 10 equals 5v, and that final velocity comes out to be 2 meters per second. So he's going to be moving at positive 2 meters per second. Now what I want us to look at, and it's pretty easy here, we're going to write it in a different color anyway. Orange looks good. With respect to the center of mass, this object starts going 10 meters per second, and after the collision it leaves with 2 meters per second. So we have lost speed with respect to the center of mass. Same thing here. We approach the center of mass with 10 meters per second velocity. We leave the center of mass with 2 meters per second. We have lost some speed with respect to our center of mass. This is very similar to what we saw going on with the ball that we threw up against the wall. So the last one that we're going to talk about, and the one that's we can actually do stuff with, is the elastic collision. So for this elastic collision, again, we're starting off, probably getting tired of writing down this same mass. We're starting off with our 5 kilogram mass, moving this way at 10 meters per second towards a 5 kilogram mass moving at 10 meters per second. And we know here that the velocity of center mass is 0. So for this elastic case, afterwards, they're going to hit and they're going to bounce off. You can probably guess what's going to happen. The velocity of center mass is still 0, 5 kilograms. We're going to move back with 10 meters per second, and this one is going to move forward, 5 kilograms, at 10 meters per second. In this case, in the elastic case, with things bouncing perfectly off of each other, do a different color for emphasis, we see that an object loses no velocity with respect to the velocity of the center of mass. Okay. This is how we are going to look at collisions. Perfectly inelastic, the object sticks and they lose all velocity with respect to the center of mass. Regular old inelastic, they stick, they hit, and they lose some speed with respect to the center of mass, not all of it. And then for elastic, they lose no velocity with respect to the center of mass. Now, we will, on Monday in class, look at some applications that we can do with elastic collisions. But I just wanted to look at a way to talk about these collisions.